In today's video in pharmaceutical chemistry, we'll be looking at order of reaction. Now, in our last class, we talked about the rate of reaction or reaction rate on chemical kinetics. Now, the order of reaction is the sum of the exponents of the concentration terms that determines the rate of reaction. That is the number of atom or molecule whose concentration determines the rate of reaction. Now, we know that when A reacts to B, it forms the product, right? As you can see from the equation above, that A has a number of molecule designated as small letter A, and B has a number of molecule atom designated as small letter B. And from the law of mass action, rate is equals to the product of the rate constant K times the concentration of A raised to the power of the exponent, which is its molecule, small letter A, multiply or also together with the product of the concentration of B raised to the power of its molecule or its exponent, small letter b. Now, the order of reaction is the sum total of the exponents. An example is the esterification reaction of ethanoic acid reacting with ethanol to form an ester and water. As you can see, the rate is equals to the rate constant K multiplied by the reacting species, the concentration of the reacting species. Don't forget that concentration is denoted by the square brackets. Now, the order of reaction, the as you can see, is 2. 1 plus 1 is equals to 2, since the individual sum of their exponents is 1. Now, the overall order is actually a second order reaction. For the rates of reaction and their equation, the rate of reaction basically is measured or determines of how fast the reaction proceed, how fast the concentration of one of the reactants is falling, or how fast the product is forming. The unit is given as mole per dm cube per seconds. Recall in our last video that some reactions occur faster than others. Some reactions are slow, some reactions are fast, some reactions are too fast to actually be measured. Now, we have three order of reaction. We have the zero order, we have the first order, we have the second order. For advanced level, we have the third order. But as you can see here, the rate of reaction is directly proportional to the concentration of the reactants. If the reactants is independent of the rate of reaction, the concentration of the reactants is independent of the rate of reaction, is a zero order. If the rate of reaction is proportional or dependent on the concentration of the reactant, is a first order. And if the rate of reaction is proportional to the square of the concentration of the reactant, it's second order. Let's look at each and every one of them individually. Zero order for a start. For the zero order reaction, the rate of reaction is independent of the concentration of the reactant. That means the rate of reaction is constant. It proceeds at a constant rate. Now, when we say rate of reaction proceeds at as a constant rate, we can see that the sum of the exponents is equals to 0. What you just need to get here is to have it in your mind the integrated form of the equation AT minus AO is equals to KT. Now, don't forget that the zero order equation, the integrated form ought to be in concentration. So don't mind what you are saying above, but just know that AT is the concentration of the reactant at a particular time t. AO is the initial concentration of the reactant. K is the constant and T is the time. Now compare it to the linear equation y is equals to mx plus c, and you can see what is the slope, the y-axis, the x-axis, and the constant. Now looking at the zero order reaction from the graph, we can see that the rate is independent of the concentration. The rate is constant. When the rate of reaction or the reaction rate is being plotted against the concentration of the reacting species or the reacting particles, you can see that it's constant. Some drugs undergo zero order, rate of reaction. Their elimination from the body undergoes zero order. The rate at which they are eliminated is independent or does not depend in the concentration of drugs in the body. So, example, you take 100 milligram of paracetamol, for example, and paracetamol is to undergo zero order reaction. It to be eliminated a at a constant rate, whether you take 100 milligram, 50 milligram, or 10 milligram. That is what zero order rate of reaction is. And if you can plot the linear graphic, you see a downward slope in respect to time. Here we see that hydrogen peroxide, the concentration is decreasing in respect to time. So don't forget that zero order, the graph is a downward slope. It does not undergo any curve. It's just a downward slope straight down. Now let's move to first order. Talking about the first order kind of reaction, here we are looking at where the rate of reaction is proportional to the first power of the concentration of the reactant, and it may be expressed mathematically below. When we have reactant A plus B giving our products, and of course, according to the law of mass action, rate is equals to K, A raised to power A times B raised to power B, and the order of reaction A plus B is equal to 1. Now, this first order reaction is when the concentration of the reactant is dependent on the rate. So don't forget that the integrated form again is the natural logarithm of the concentration of the reactant at a time t equal to the natural logarithm of the concentration of the reactant at the initial, that's AO, the initial concentration, or A0 minus KT. Comparing it again to y is equals to mx plus c, and then you can see on the graph that for first order, plotting the natural logarithm of the reactant against time, you can see the slope at which it follows for first order kind of reaction. Similar to second order, but you would know when a reaction is first order if you are going to use the natural logarithm of the concentration of the reactants. Almost all drugs or most drugs undergo the first order kind of reaction. Now, when you are looking at the rate of reaction, according to the law of mass action, rate is proportional to the product of the concentration of the reactant species. For A, which is of course the first order, as an exponent of 1. For B, which is of course also in first order, as an exponent of 1. The overall reaction will now be 1 plus 1, that means 2. So the overall reaction of this reacting species is going to follow the second order kind of reaction. Don't forget that order of reaction is A plus B, the sum of the exponents. So when you add all the exponents together, it will give you the overall reaction order. Don't forget again that the order of reaction is the sum or the sum total of the exponents as given in the law of mass action, of which rate is directly proportional to the exponents of the product of the reacting species, their concentration, which is denoted in a square bracket. Now, if there's a change in the reactants, of course, there'll be a change in the rate. So when doubling either the reactants, it results in the doubling of the rate. So the rate of reaction is directly proportional to, the concentration of the reacting species raised to the power of their exponents. So where if A is equals to 1, B is equals to 1, of course, A plus B will give the overall sum of reactions. So in this case, the sum of the two first order reactions is a second order reaction. It's a second order reaction. Don't forget that 1 plus 1 is equals to 2. So overall, that reaction is a second order reaction. Now, if the reactant is going to be doubled and 1 is unchanged, as seen in this next example. So when doubling one reactant, it quadruples the rate. So if you are doubling one of the reactants, it will also affect the rate. So if A is equals to 2, B is equals to 0, then we have the rate to be directly proportional to, you know, 2 plus 0, which is still 2. That is a second order reaction. I'm talking about second order. This is the order of reaction in which it is experimentally determined and found that the rate of reaction is proportional to the concentration of each of the two reactants or to the second power of the concentration of one of the reactants. So, of course, rate of reaction is directly proportional to concentration of A raised to power 2. And don't forget that it is the inverse as given in the integrated equation. It is the inverse of the concentration at a time t equal to the product of K and T, the rate constant, plus concentration at the initial level, that is AO. Some drugs can start with first order and then go into the second order kind of reaction if one of the reactants is actually increased, or if there's an increased dosing of the drug. Now, if you look at the second order graph, you can see an upward slope. The of course the plotting the natural logarithm of the reacting species against time. You can see an upward slope for a second order kind of reaction. And there are ways whereby you can determine if a reaction is first order, if a reaction is second order. You can determine by half-life, you can determine from the equation, you can determine graphically. So in our next video, we are going to be talking about the half-life.